For this project, we chose to do a Kaggle competition. It is called Plant Pathology 2020, which is a fine-grained visual categorization task. This competition is part of the FGVC workshop at the CVPA 2020. In the project we will distinguish different diseases on a single leaf. Current disease diagnosis based on human scouting is time-consuming and expensive, and although computer vision-based models have the promise to increase efficiency, the great variance in symptoms due to age of infected tissues, genetic variations, and light conditions within trees decreases the accuracy of detection. The dataset of this competition is provided by Cornell Initiative for Digital Agriculture. This task is a seemingly simple visual classification problem with only 4 classes: healthy, multiple disease, rust, and scab. There are 1,820 labeled images for training and 1,820 unlabeled images for testing. Kaggle will judge the performance based on the prediction results on the test set. Since it is a classification problem, we first used pre-trained ResNet 3.4 as our model and got 91% accuracy on the test set judged by Kaggle. However, we found 91% accuracy was not good enough. Then we realized it is not a simple classification problem. Instead, it is a fine-grained classification problem, which means the images of different classes are quite similar to each other. After doing some research about fine-grained classification, we determined to use a novel model that called Weakly Supervised Data Augmentation Network. This model is designed to tackle fine-grained classification problem. We have listed the reference at the bottom of the slides. We will go through details about this model in the next few slides. During the first stage of the project, we applied pre-trained ResNet 3.4 and got 91% accuracy on the test set. Our basic transform stack includes resize, to-tensor and normalization. These are applied to both the training set and validation set. By inspection, all the images in the dataset have size 2048 x 1365, so the first step is to resize images. Considering the frequent used 5 crop will multiply the batch size by 5 and increase the burden of RAM, we chose to use random crop. After testing on the validation set, we finally found random horizontal flipping and color jitters will lead to better performance on test set. Our task is a fine-grained visual classification (FGVC) problem, which aims to classify the subordinate level categories under a basic level category, such as species of the bird, model of the car and type of the aircraft. In our project, we are required to distinguish between many diseases on a single leaf. Many papers have proved that traditional state-of-the-art CNN architecture, e.g., ResNet, GoogleNet, DenseNet, can only achieve moderate performance because it is relatively difficult for them to focus on the subtle differences of object as parts without special design. The training process includes 2 parts. First is weakly supervised attention learning. For each training image, attention maps will be generated to represent the object as discriminative parts by weakly supervised attention learning. Second is attention-guided data augmentation. One attention map is randomly selected to augment this image, including attention cropping and attention dropping. Finally, the raw and augmented data will be trained as input data. The testing process also contains 2 steps. First, object as categories probability and attention maps will be outputted from raw image by part A. Secondly, object will be located according to part C and then be enlarged to refine the category's probability. Finally, the above 2 probabilities will be combined as the final prediction. During training and testing, the object as location annotation is not available. In this method, we adopt weakly supervised learning to predict objects' location distribution only their category annotation. We first extract the feature of image I by CNN and denote F as features maps, where H represents height, W represents width, and N represent number of channels. The distributions of objects' parts are represented by attention maps, which is obtained by the formula, where lowercase f is a convolutional function. Here f contains learnable parameters. After representing object as parts by attention maps A, the paper proposed bilinear attention pooling (BAP) to extract features from these parts. We element-wise multiply feature maps F by each attention map AK in order to generate M-part feature maps FK. Then, We further extract discriminative local feature by additional feature extraction function G, such as global average pooling (GAP), global maximum pooling (GMP), or convolutions, in order to obtain kth attention feature FK. And finally, we can represent the part feature matrix by AM times N matrix. The second innovative point is the attention-enhanced data augmentation during training and testing. Random data augmentation can be low efficiency because it may introduce some background noises. However, with attention maps, data can be more efficiently augmented.